A pulsar once spit a beam of radiation so powerful it reset every GPS satellite on Earth, and that was just the outside. Inside, physics stops making sense in ways your brain wasn't built to handle. A lot of people think pulsars are just spinning stars, like cosmic lighthouses that blink on and off. That's not what they are. A pulsar is what's left after a massive star collapses. The entire core, with more mass than the sun, gets crushed into a ball about 20 kilometers across. That's the size of Manhattan, the whole island. Now imagine squeezing the sun into that space. That's a pulsar. And it spins. Fast. Some of them rotate hundreds of times per second. But let's say you could somehow survive the trip there and stand on the surface. You couldn't. Not even close. The gravity alone would crush you to the thickness of an atom before you even registered what was happening. The surface gravity of a pulsar is 200 billion times stronger than Earth's. If you were somehow hovering 1 meter above the surface and let go, you'd hit the ground in a microsecond. Not a second. A millionth of a second. And when you hit, you wouldn't splatter. You'd just stop existing as anything recognizable. Even the atmosphere can't escape. Most objects in space don't have atmospheres because gravity isn't strong enough to hold on to gas. A pulsar has the opposite problem. The gravity is so strong that the atmosphere gets crushed flat against the surface, like paint. It's only a few centimeters thick. That's it. A few centimeters of superheated gas pinned down by gravity, so extreme it warps space itself. The surface temperature sits around 1 million degrees, hot enough to vaporize anything. But the gravity doesn't care. It holds everything down anyway. The surface itself is made of crystalline iron, not regular iron. This is iron compressed into a lattice so perfect and so dense that it makes diamond look soft. A teaspoon of this material weighs as much as Mount Everest. The entire mountain, scooped into a spoon. And if you somehow place that spoon on Earth, it would punch straight through the ground and keep going until it hit the core. Mountains technically exist on a pulsar, but they're not mountains in any way you'd recognize. The tallest peaks are only a few millimeters high. Anything taller gets crushed flat instantly. Gravity doesn't allow imperfections. The surface is smooth, hard, and perfectly unforgiving. You could stand on it for less time than it takes light to cross a room. That's just standing on it. Now we go deeper. And this is where your sense of what matter can even be stops working. The crust starts about a kilometer below the surface. That might not sound deep, but in that 1 kilometer, density increases by a factor of 100 million. The top of the crust is already denser than anything on Earth. The bottom is denser than anything your mind can process without breaking. Imagine a jungle gym made of iron. The bars are atomic nuclei, and the spaces between are filled with electrons flowing like water. Now compress that jungle gym until it's stronger than anything in the universe. That's the crust. The crystal structure is so perfectly ordered, it makes diamond look like loose gravel. And it's not one type of iron. As you go deeper, the nuclei change. They pack in more and more neutrons because the pressure demands it. Neutron-rich iron, then nickel, then elements that don't exist anywhere else because they'd fall apart instantly without this kind of crushing force holding them together. At the top of the crust, 1 cubic centimeter weighs about 1,000,000 grams. That's a ton. A sugar cube that weighs a ton. You descend a few hundred meters, and that same cubic centimeter now weighs 100 million tons. That's the weight of 15,000 aircraft carriers, compressed into something you could hold between your fingers. If you could hold it, which you couldn't, because your fingers would collapse into neutrons. Here's where it gets strange. The crust is unimaginably hot. Millions of degrees. By every rule you know, it should be liquid, molten. But it's not. It's solid. Rock solid. The pressure is so extreme that it overwhelms the heat. The atoms can't vibrate. They can't move. They're locked in place by the sheer weight of everything above them pressing down. Temperature doesn't matter anymore, only pressure. This is why those millimeter mountains exist. The crust is rigid enough to support them. Barely. Anything taller, and gravity crushes it flat. The surface isn't smooth because it's polished. It's smooth because nothing else is physically possible. And the strength. The crust of a pulsar is billions of times stronger than steel. You could take a chunk of it if you could somehow extract it and keep it intact, and it would support the weight of a mountain without bending. The molecular bonds are so tight that breaking them would require more energy than a supernova. This is the hardest substance in the universe. Nothing comes close. But here's the part that breaks your brain. This incredibly rigid, impossibly strong crust is floating on top of a liquid that has zero viscosity, zero friction, literally zero. The crust is the most solid thing in existence, and it's sitting on top of something that flows without resistance. And that's where things go from weird to physically impossible by Earth standards. Below the crust, you hit the outer core, and this is where matter stops acting like matter. It becomes a superfluid. That word sounds made up. It's not. A superfluid is a state of matter that has absolutely zero viscosity, zero resistance to flow. It doesn't act like any liquid you've ever seen because friction doesn't exist for it. Think of stirring honey versus stirring water. Honey resists because of friction between the molecules. Water resists less. A superfluid has zero resistance. It's like stirring something that doesn't know you're stirring it. It just keeps moving however it was moving before, forever. If you could pour it into a cup, it would climb the walls, spill over the edge, and drip upward. Not because it wants to, because nothing stops it. Gravity pulls it down, but friction is the only thing that keeps liquids from doing whatever they want. And friction is gone. Inside a pulsar, neutrons pair up and form this superfluid. They shouldn't pair up. Neutrons are identical particles. They should repel each other. But under this kind of pressure, quantum mechanics takes over and forces them together anyway. They move as one. Billions of trillions of neutrons acting like a single flowing substance with no resistance. And right next to it, protons do the same thing. They form a superconductor. Electricity flows through them with zero resistance. The entire outer core is a sea of particles that have stopped obeying the rules. Now here's where it gets observable. Pulsars slow down over time. They lose energy through radiation, and their rotation gradually decreases. But the superfluid inside doesn't care. It keeps spinning at whatever speed it was spinning before, because nothing can slow it down. No friction, no drag. So the crust slows down while the core keeps going. The two layers decouple. They spin at different rates. Then, suddenly, they couple again. The superfluid dumps its angular momentum into the crust all at once. The pulsar hiccups. It spins up. When this happens, it's like Earth suddenly rotating 100 times faster in 1 second. Astronomers call these events glitches. The Vela pulsar does this every few years. We've measured it. We've watched the spin rate jump and then slowly decay again as the layers pull apart. It's proof that there's a frictionless ocean inside these things, doing exactly what the physics says it should do. That's the outer core. Impossible fluids doing impossible things. But we haven't reached the center yet. And at the center, matter might not even be matter anymore. The inner core is where we stop knowing and start guessing. Nobody has seen inside one. Nobody can. The pressures there are beyond anything we can recreate in a lab. Beyond anything that exists in normal stars. We're talking about pressures around 10 to the 35th pascals. At that level, you could crush the entire Earth into a ball smaller than a football stadium. So what's actually in there? We have theories, 3 main ones, and they all sound insane. The first possibility is simple. Just more neutrons. Denser than the outer core, packed tighter, but still neutrons. Boring by pulsar standards, which means unimaginably extreme by any other standard. 1 cubic centimeter at the core might weigh more than a mountain range, but it's still neutrons doing neutron things. The second possibility is quark matter. Imagine crushing atoms so hard that the neutrons themselves shatter into their smallest pieces. Quarks. It's like crushing a Lego castle until the individual bricks break apart into the plastic molecules. Except if you did that, the plastic might become something that's never existed in nature. Quarks are normally locked inside protons and neutrons. Always. They don't exist freely in the universe. But at the center of a pulsar, the pressure might be strong enough to rip neutrons apart and create a soup of free quarks. No protons, no neutrons, just quarks floating in a sea of themselves. The third possibility is stranger. Strange matter, that's the actual name. Quarks come in types: up quarks, down quarks, and strange quarks. Normal matter uses up and down. Strange matter includes strange quarks in the mix, and some physicists think strange matter might be the most stable form of matter in the universe. More stable than atoms. More stable than neutrons. If that's true, then the core of a pulsar might be a ball of strange matter sitting at the center, completely stable, completely inert. Some theories even suggest strange matter could convert normal matter on contact. Touch it, and you become it. But that probably doesn't happen. Probably. The truth is, we don't know. We can't drill into a pulsar. We can't simulate these pressures. The core is hidden behind layers of matter so dense that nothing gets through. No light, no particles, no information. We're stuck guessing based on the math and hoping the universe doesn't have surprises we haven't thought of yet. We can't see the core, but we can see what it does. And what it does is turn a city-sized ball into the universe's most powerful magnet and the most precise clock ever found. All that density spinning that fast creates magnetic fields strong enough to warp reality. A pulsar's magnetic field can be 100 million times stronger than Earth's. The strongest ones hit a quadrillion times stronger. If a pulsar appeared at the moon's distance, it would erase every hard drive on Earth instantly. It would rip iron from your blood. The magnetic field alone would kill you from 200,000 miles away. That field channels particles into narrow beams shooting out from the magnetic poles. Those beams spray radiation across space like water from a fire hose. And because the magnetic poles don't line up with the rotation axis, the beams sweep around as the pulsar spins. It's a lighthouse. The beam rotates. If Earth happens to be in the path, we see a pulse. Blink, blink, blink. We're not special. We just happen to be standing where the light hits. The fastest pulsars spin over 700 times per second. That's faster than a kitchen blender. Faster than a jet engine. Except it's not a blade. It's the entire mass of the sun rotating in a space the size of a city, and it doesn't wobble. It doesn't slow down unevenly. The rotation is so stable that pulsars are more accurate than atomic clocks over short time periods. Astronomers use them to test Einstein's equations, to detect gravitational waves, to measure the fabric of space itself. A collapsing star becomes the universe's most precise timepiece. We've found thousands of pulsars now. Some pulse once per second. Some pulse so fast the beats blur together. Millisecond pulsars. They've been spinning for billions of years, and they're still going. Still broadcasting. Still cutting through the galaxy with beams of radiation, so focused you could navigate by them. And the wild part is what this all teaches us. Matter doesn't have to behave the way it does on Earth. Atoms can be crushed into neutrons. Neutrons can flow like water with zero friction. And maybe, at the very center, matter stops being matter at all. It becomes something new. Something we've never touched or seen. Something that only exists when you take the mass of a star and squeeze it until space itself gives up. You'll never visit a pulsar. You'll never drill into one or crack it open to see what's inside. But you can look up on a clear night and know they're out there. City-sized spheres of impossible physics spinning in the dark, broadcasting their existence to anyone who cares to listen. And we're listening. We're catching those pulses. We're learning from them. And every time we do, the universe gets a little stranger and a little more beautiful.